Last talk of the day. I'll try to finish on time so you get to after party beer, whatever, afterwards quickly. So I'm from Vienna. I always explain it like the city of fatty foods, beautiful architecture, and classical music. That was the only way how we could actually win anything in music nowadays. Yeah, so I work for Elastic, the company behind Elasticsearch and Logstash, Kibana, Beats. I'm in the infrastructure engineering team, so we do stuff like AWS, Docker, Ansible, Jenkins, even though we always say it's more like Jerkins because it's such a jerk. Yeah, and then I kind of pipe, that is a Unix pipe, that into developer advocacy, so I'm doing lots of conferences just talking about all the good stuff we're kind of doing. So, who uses databases? I guess pretty much everybody. That is a good start. Who uses search? Okay, that is also quite a lot. Who uses Elasticsearch already? Okay, that's quite a few. Let's see if you can learn anything new. If it's all too basic and boring, let me know and we can make it more advanced. So let's see. Let's start with something more practical. So we have, is that large enough? I hope that scales nicely up. Okay. We have written this demo application. While it is on the internet, unfortunately, you cannot access it. It is behind password protection because we built the system, but the data and the pictures and everything is from Zalando, and they've only provided them to us for demos. So unfortunately, you cannot use it yourself. But the nice thing is we have this search bar here, and I can just start searching for something. So assume you're going to your favorite shopping site and you just look for something. And I'm looking for a white shirt. And then automatically it will, as you can see, I have tried this. Your search is my previous search is white shirt. I have done that. And then we have other suggestions. Like, this is pretty much what full text search should give you. What makes this page kind of different to most others is that we have this little tool here, and that shows the query that is running in the background. So this is the Elasticsearch query that is running in the background. We'll get into those details a little later. Let's just see how search works. So I've pressed enter. Page is loading. Hopefully Wi-Fi works as expected. Yes, it does. And you can see, I have not reset my filters. So what you would get by default is, yes. So if you search for white shirt, in our search example, that is the first thing you get. And as you can see, these are not white shirts. So that search is not that great yet. The problem is, it's not just the technical side, you need to implement something, but it's more about the intention of the user. So you kind of need to guess what does the user really want to see, and what is relevant for that specific user. So in our tool here, we have multiple things. So on the first, we have on the right-hand side here, so I can kind of fold and unfold that. I have the properties of our search here. And the first thing that is a problem is that we have this query type best, which sounds very good, but in our case it's not. Because what we have is we have two search terms, white shirt, and we're searching on multiple fields. We have a title, we have a description, we have multiple other fields. And then the question is like, what are you looking for? Are you looking for all the search terms in one field, all the search terms over multiple fields, all of them in the same field? What do you expect is kind of the perfect combination? And what best does, best only looks at the best field you have in each document and ignores the others. And in our example, that doesn't work that well. If I switch that to, we could either do most or cross, they should be pretty similar. If I run that query afterwards, so cross basically means I take my term white shirt and search them over all the fields I have stored. And that, in my example, gives much better results because this looks more like the shirts I'm looking for. And since I have logged in, it knows I'm male, so all of the examples I have here are male as well. So it can filter down on stuff like that. And then you could boost stuff. For example, we could say the name is not that important. I'm more interested in the description. So I can say this is 10 times as important as it was before, or as the name field. And if I apply that one, it will break pretty badly again if it's loading. Come on, apply. Apply. Well, let's try different search term. Like, let's just search for white cotton shirt. And if I search for those, yeah, that is not really what white cotton shirt is. If you search gives you that back, your users are probably not that happy with what you do. And also you can see, I'm getting female products now, so that is not really what I want. So I'm saying, okay, I want that back to where it was. I want to have, I'm switching over to the advanced one, and we should have a gender bias, and I'm saying I have a full gender bias, so since I'm searching for myself, I only want male products. And if I apply that again, that page is not fully responsive. Let's load again, and come on, show yourself. Now, so we are where it cross. We have the gender bias. Yeah, let's put that to 100%. Let's apply that. I also want to get that down again. And hopefully, once I apply that, now it's loading. Hopefully, all the stuff is making more sense now. So I only get male shirts again. And all of them are white shirts. And I hope all of them are cotton as well. So there is a lot of fine-tuning, and that totally depends on your use case. So I cannot give you kind of the rules like you need to boost this field, and this is important, and this is not important. That is the part I cannot tell you. But what we can do now is we can kind of jump a bit more on the tech side to see what is actually going on behind the scenes here. So I will just continue here. The first thing that makes full text search very different to databases is that databases are very much black and white. You just store stuff and want to retrieve it. Whereas in full text search, you more have these concepts you're looking for. I don't really care about singular, plural, or any flexions or anything. I just want to have that concept. So I'm searching for white shirt, and if it's white shirts, or maybe you have, I don't know, light shirts instead of white, you probably want to find the same thing. So the first thing you normally do is you kind of normalize what you have as the import and then store those normalizations. And that makes search afterwards very fast. So what this does is we have Apache Lucene in the background. That is what kind of stores the data. There's no other database involved. That is what is storing the data on disk and actually doing the querying. And then you have Elasticsearch kind of around it, that is the wrapper or the shell that is providing a REST API, the query DSL, and the distribution of the data for you. But the features I'm mostly interested in now are actually plain Lucene features. It's just like, how does this search work in the background? If you want to run that, so I'm switching away from my demo, so you can actually try that yourself. You can either run it, obviously, in the cloud. Everything needs to be in the cloud. Like, we have a cloud offering there as well. So you get a free test account if you just want to spin up a demo. That's very nice for that. Or the other thing that everybody needs to do nowadays is Docker. And I always compare it like, for me, the Docker logo is more like this. Like, you're the little fish, and that is basically the Docker container that tries to eat you as a whole. Yeah. That is the minimal Docker setup, and this is what I'm running my demo on. So we basically have Elasticsearch, and we have Kibana, that is just the front end that we can run queries in a nice fashion, and just start throwing stuff at Elasticsearch and see how it reacts to what I'm trying to do. So that is the minimal Docker compose file that you can use. Who knows this quote? Like, who knows Star Wars in English? Anybody knows what he says when he makes that hand movement? Yes, exactly. These are not the droids you're looking for. I've just added this emphasis, and this is our example text. So we want to store that in Elasticsearch and see what actually happens behind the scenes. So the first thing is normally you throw out the HTML, the markup, because nobody is searching for the EM tag. You're not interested in that. We're just stripping out any formatting. Next up, we're tokenizing. Tokenizing basically means you just extract the words you have. So I've added a bit more space between the words. You see the dot at the end is gone. I've just all the independent tokens now. Then you lowercase. Because when you search, you normally don't really care if it's upper or lowercase. Like if you type in shirt, upper or lowercase, it shouldn't make any difference. Though, as we've seen in the previous talk, like on the ASCII characters, upper and lowercase makes a difference. So we just lowercase everything so search is faster afterwards, and you can just use the lowercase. And then is where kind of the real magic happens. Then we remove the so-called stop words. Stop words are just very common words that appear in nearly every text, but nobody searches for them because they're so common. So these are not the droids you're looking for. Like those are super common words. They appear everywhere. So we're just removing them. So what we have is droids you looking. Those are the non-stop words that remain. So that is what we will put into Elasticsearch afterwards. But before we do that, we still stem it. Stemming basically means cutting off the word ending. I don't speak Russian, unfortunately, but I have been told that this is much more complex in Russian than in English, because you have different formats and flexions. English is a very simple language. You basically just cut off the ending, and then you get kind of a normalized form. So droids you looking becomes droid you look, and this is the stemmed form. There are different stemmers. We're using Snowball. It's open source and widely used. Doesn't make that much of a difference. So you can just throw that against Elasticsearch and run that query. These are not the droids you're looking for. And we can just do that live because it's much more fun to do stuff live. And if you have any questions, just stop me. I guess this is big enough that you can read it, right? Big enough? Good. So I have, these are not the droids you're looking for. And if I use, so this is basically a curl x get localhost 9200 / analyze, and then that is the body. This is just part of Kibana now. It's kind of a nicer way to interact with Elasticsearch. You don't need to provide the server. It has syntax highlighting, it has auto-completion, and it just shows you the results on the right-hand side. So what I'm doing here is I'm running _analyze, and _analyze is just running this field text against this analyzer and shows you what would happen. I'm not storing anything here, I'm just analyzing that, and that is what Elasticsearch would then actually store. Can make that a little bigger. So if I run that, these are not the droids you're looking for. What we have is droid you look, what I told you before. Plus it knows the start and the end. So for example, if you, in your search highlight, in the original document, want to highlight the word that you just found, like if you want to highlight droid, you know this is the position. So you can highlight that position in the text. And then we have, those were the offsets. And then we have the position. The position is just at what point in the sentence, or what place in the sentence that has. That is important if you're searching for phrases. Because then you're just searching for droid you, which is a weird phrase, I know. But to search that, you just search for where does droid and you appear, and where is first droid, and you is just the next position. So that is why we store the position. So this is what actually Elasticsearch would store in the background and put into an index. And you can make this a bit more advanced and just define what you're doing. So here I have, these are not the droids you're looking for with my emphasis. I'm stripping out HTML. I'm lowercasing it, I'm stop wording it, I'm using the snowball stemmer. So I'm explicitly defining all the steps I'm doing. And it's giving me exactly the same result now. It's just like I have this emphasis, and that has been removed. Okay. I do have a Russian example. Before we jump into Russian. These are, by the way, the stop words. So they there are very few words, but as you have seen in our first example, they make quite a big impact. Like, it has removed more than half of the words in my "these are not the droids you're looking for," but it's only, I think, 30 or something like that terms. So only these are the stop words, only these will be thrown out by default. So, I have been told that this is the same phrase in Russian. These are not the droids you're looking for. What do you think remains if I analyze that with the Russian analyzer? Yeah, so what happens is, I cannot read it unfortunately, but this is what happens. If you don't believe me, we can actually do it just live. So I've just switched to the English analyzer now. And yeah, these are the words that remain. I think what is also removed here is the not, right? This basically says, these are the droids you're looking for. The Russian version, the second one is? Sorry. Yes, because I used the English analyzer here. That was what happens if you use the wrong analyzer. So these are not, yeah, there is no not in there, right? So one kind of important thing you need to keep in mind is full text search does not understand your text. It's not natural language processing. It doesn't know the meaning. If these are the droids you're looking for or these are not the droids you're looking for, it doesn't know that. It's just taking words, like the tokens, and applying rules to them. It's not as clever as you might think, but it still works pretty well for full text search if you just work on these tokens. And what I wanted to show you is, if you use the wrong analyzer, like we're using English on Russian text, you will just pretty much get the original, because there are no rules that apply. So you will need to set the right analyzer. So if you want to look up the Russian stop words, those are quite a lot. They're hidden deep down in the Lucene source code. But that is where you can find them. Yeah, that happens when you use the wrong analyzer. What Elasticsearch by default does not do is it does not detect your language. So you need to know what the language of a text is. Otherwise, it will just use whatever you tell it to. But one of my colleagues wrote a plugin that can actually detect, or it's basically an educated guess. It doesn't know, but based on some specific features, it will try to detect the language of a text that you give it. And then it will tell you, okay, this is English, this is Russian, and then you can index it correctly based on the language. These are all the languages that we support in the current version. Like you can see, Western languages are widely supported, even stuff like Latvian. What we don't have is Slovenian and Slovakian yet, because, I don't know, there doesn't seem to be, nobody picked up the work and basically did that. And how does a language get added? For example, what is missing in that list, the latest language that was added, I think, was Ukrainian. So that was added first. It needs to be added to Apache Lucene. Once Lucene does a release, we can integrate that release into Elasticsearch. And when we expose the API and we do another release, then that language is supported. So yeah, that is kind of, if you have a language that is not supported, that pull request could show you how you could get in another language. For example, Belarusian is not supported yet, and yeah, people in that community have the idea of adding support for it. First, you need to add it to Lucene, and then you need to add it into Elasticsearch that is actually usable. And there are totally language-specific rules. I have left out Russian since I cannot even read it, but you can see you can cut off stuff at the end. You can cut off stuff at the beginning, and in German we have these weird umlauts and this S thingy. They are just kind of moved down to the ASCII version of that. So these are totally language dependent, and I'm sure Russian has also lots of rules what to actually do with words, how to process them. Okay, we're moving back to English so I can participate as well. Obi-Wan never told you what happened to your father. What do you think happens when I run that through my pipeline? Or actually, we can just do that live. Where do I have it? Obi-Wan never told you what happened to your father. What do you think remains when I run that? So we get Obi-Wan. By default, the dash is just tokenizing characters, so you get Obi-Wan separated. Never told you what happened your father. In this example, we don't have that many stop words, so nearly everything remains. Or we have, no, I am your father. What do you think remains here? Yeah, unfortunately, I am your father. And it totally changes the meaning again. So it doesn't know what your text is, because no, that is the only stop word in here. And if you take these three texts, what Elasticsearch would actually store in the background is this. So it is taking all the words you have at the end, like after you run it through analyze, all these words would be put into an index. It is sorted alphabetically, and then you have all the documents. So assume we had the document 1, 2, and 3, and you just store like how many times did the token appear and at what position in the text. So you then know how many times did father, for example, appear, and did it appear in a specific document, and if yes, at what position. So that is kind of the data structure that is stored behind the scenes in Elasticsearch. And now we can actually start storing something, because so far we have just used this analyze, and it's just showing you what would happen behind the scenes. So I have an index called Star Wars. An index is pretty much a database in the relational world. And I'm defining synonyms here. The first thing I'm defining is droid and machine is the same, and father and dad is the same. These are my synonyms, and I store them under my synonym filter. Then I define my analyze pipeline, and I do HTML strips, standard tokenizer, lowercase stopword, snowball, and after the stemming, I add my synonym filter. Here, my synonyms will be put in. And then I say I have a type called quotes. Think of a type, it's like an enumeration type. It's like you could have different things in the Star Wars index, even though types will go away in the future, so don't rely on them too much. But that is something we can discuss afterwards. And then I'm saying under the property quote, I expect something of the type text. So this is like text in a relational database. And this will be analyzed by my analyzer, which I have defined up here. So I insert that. This is pretty much the schema you would have in a relational database. We just call it mapping. So we have created that. We could look it up, but isn't that interesting. Instead, I will insert my 3 documents we've discussed already, so you know what will be stored in the background. You can easily retrieve that, but that is pretty much what a database does. So if I say quotes, Star Wars quotes 1, that is where I stored my first quote, and it would just return you the entire document. You can even use it pretty much as a database. You can just say source, I just want the original one, and that is just what you have put in. So you can basically use it as a database, but that is not what the power of full text search is about. So now we can actually jump into the searching part. So the first thing is, who knows what that query does? Since we have Elasticsearch users here, what would the SQL equivalent to that? Yeah, exactly. Select star from Star Wars. So this is just selecting all 3 documents I have inserted. That was simple. Again, there is not much full text search features are involved. Now we are searching for droid. Will this find anything? Yes, the first document. Even though we had droids, it will be stemmed down to droid, so that should find something. So if we run that, you see, okay, we had 1 total hit, and you can see these are not the droids you're looking for. So yes, we found that. If I search for this one, so I have a query, I'm matching on the field quote, and I'm searching for dad. Will this find anything? It will actually find the second and the third document, because I am your father, because we have defined dad and father to be synonyms. And the same thing for Obi-Wan never told you what happened to your father. So since dad and father are just synonyms, it will, if it finds that here in the query, it will just, so you have two options. You can either do that at query time or at insert time. In that example, I think it's done at insert time, so it will be just under the, like, the hit will be recorded under father and dad, so if you look up dad, it will find the father example as well. You can also do stuff like phrases. So since I have no I am your father remained, so that should be available as a phrase. So we require all these 4 terms to be in exactly that order in any document. So this will only, or we could just shorten it down to your father. And it will find I am your father, and never happened what to your father. Okay, yeah, it will actually find both, but if I search for the phrase I am your father, it will just find that no, I am your father. What do you think will happen if I say I am your loving father? Will that find anything? This document? It doesn't find anything because it's a match phrase, so it requires I followed by am, followed by your, followed by loving, followed by father, and we don't have a loving in there. So that doesn't find it. But what you can do is, or we could, yeah, we can do it not your father or loving, we can do loving father again. If I type it correctly. We can add something like a sloppiness, so we can say there can be up to 1 term can be in between. Like, I'm looking for that phrase, but if there is a minor variation, I'm okay with that. This sloppiness or slop factor, what? Why I am your father? That is interesting. Never try in a demo stuff you haven't tried before. Why isn't slop? That is interesting. Love gets, that will be stamped down to LOV. That is interesting. Why is that not working as I expected? Well, that's tough luck. No, because it's the wrong word, and the sloppiness just defines there is a, because the not will be stamped out. If I have not your father, that will be removed, and we have just a missing word here. So yeah, that's why that one works. Fair enough. Okay, and then we have more advanced concepts. For example, we have fuzziness. So if I don't know how to spell Obi-Wan, and I just spell it Wan with a V instead of a W, if I remove this one here, obviously it will not find anything, because it doesn't exist in the index. But I can define fuzziness, which is basically a Levenshtein distance. And I could define a numeric value, so I could, the default is 0. I could set it to 1, 2, 3, whatever. So you could have, if I set it to 1, you could have 1 character different, 1 too many, or 1 character missing, and you would still find something. So with auto, if you have up to 2 characters, auto fuzziness would be 0. 3 to 5 characters would be fuzziness of 1, and more would be 2. So if I search for that, it will still find my Obi-Wan, even though I have my I have mistyped it here. And that again is one of these decisions, like, do you want that in your query results for your users, or do your users expect this fuzziness, or do they want only exact matches to be found? Like, we provide the capabilities, but how you actually do it is up to you. And just to show you how this works, because this has a very nice, this feature has a very nice feature or history. So in the beginning, for the FuzzyQuery, we just used a brute force approach. We just kind of generated every possible combination and just searched for all of them, which was very slow. With a fuzziness of 1, like, you can imagine, like, how many letters can be different or added or removed. So that is a lot of combinations. And there is an academic paper that nobody really understood, which explained that you can do it much more efficiently. And then they found the Python implementation. Also, nobody really understood. And then they kind of ported the Python implementation to Java. And that is the current implementation. And it works, and that blog post by one of my ex-colleagues actually explains how that came to be. So now they're using a Levenshtein automaton, which is actually very clever. So assume you have the term food you're searching, and you have a Levenshtein distance of 2. So you could have 2 letters in the beginning. Like if you just have a direct match, it would be like every direct match is horizontal. Like you match an F, you match an O, you match another O, you match a D. That is kind of, oh, you have matched everything. We don't need those 2 wildcards. We're ending here. We have found something. And then you always have like, oh, I have found F. I have, I don't know, a different letter here. And then I have food. And then I don't need the second degree of flexibility. So this is kind of the automaton. Like it's a full mesh of all the combinations you could have with a Levenshtein distance of 2. And this is much better than brute force. It's fewer combinations you need to actually search for. This is how this happens in the background. Or you could do that in a relational database. But you can imagine how much fun that is if your terms are getting longer and how performant that will be. Okay, one thing we have not really talked about. So we always had this score here, underscore score with some numeric value, and I didn't really explain where that is coming from. That is another feature that makes search different to databases, that this score attribute is kind of a quality, or yeah, the score, how well does that match my query. So what we're using in the background is called TF-IDF, term frequency inverse document frequency, if you search for one term. We have kind of replaced the implementation in the background with something called better match 25 now, but it doesn't really matter. It's just minor changes. So you have 3 attributes that are kind of interesting and make a difference. The first one is the term frequency. If you're searching for father and one text contains father 3 times and another term contains father just once, the text that contains father 3 times is more important than the one that only contains it once. And that would be kind of the curves. So you can see this is the number of times the term appears, and this is kind of the quality or weight that document gets. So if it just appears once, it is rather low. If it appears the term father 5 times, it is much more important. And you can see the curves between TF-IDF and BM25 have changed a bit, but the approach is the same. Like, if one text contains a term more often, it is more relevant. That is the term frequency part. Then we have the inverse document frequency. The inverse document frequency basically assumes if you have terms that appear very frequently, they are not that important. However, if you have terms that are very rare over all your documents you have, that is very important. So what that looks like is this is the number of occurrences of your term over all the documents you have in that index, or actually in that field. So if it just appears a single time, it is very important. If it appears hundreds of times, it gets less and less and less important. For example, with BM25, if a term appears more than 1,000 times, it's basically irrelevant. You just don't care for it anymore because it's so common and you would have so many matches. And the last thing is the query length norm. That is basically the number of characters in a field. And the point is, the shorter the field and it contains your keyword you're searching for, the field is more relevant, which is kind of intuitive. If you have the subject, which is very short, and your search term appears there, it should be important. However, if you have a very long text body and your term appears there, well, yes, it's amongst hundreds of other terms, so it's not that relevant. And then you can put it all together, and that is the grand formula. And you can actually see how this is working behind the scenes. So if we're searching for father and I'm running an explain, it will do my regular query and tell me the result. And then it will have this underscore explain. And then we have the value. And it actually puts together like what was the term frequency, what was the inverse document frequency, like all the factors that are contributing. So if you don't really know why something gets a specific score or why something is ranked better than something else, the question mark explain here at the end of the query that will actually show you why this has happened, and it goes into great length to show you what is going on behind the scenes. By the way, something that is weird. I'm doing a query, so I'm just reading data. Why am I doing a post here? Any guesses? What would happen if I do a get here? Like, get sounds better for reading, right? If I do a get here, it will even get me the same result. Why might I not want to use a get here? Any guesses? Yes. Yeah, it will. It should always get you the same result. Like if I run that query multiple times, you will get exactly the same. Like yeah, the took is different because that's just a timing thing. But otherwise, the result is stable. But what is different? Like get, it's not, the body is not defining get. And if you use some tools, they will not transmit the body actually if you do a get, and then your queries will not work. So I'm in my examples normally use post, but that is very much a question of personal preference or taste. Like I know some of my colleagues always use get, I always use post. You can mix them, it doesn't make any difference. It's just like, yeah, how you interpret REST. Okay, and then we have something else. You can actually provide a function how to score something. So you can provide a script, or if you use geolocations, you can say this is decaying, like the closer it is, the more important, and then it's kind of like a radioactive decay slowing down. Or you can say if something is more recent, it is more important. So you have a function where you can basically define how something should be ordered. And in my example, I'm searching for father, and I'm using a random score. So I'm basically just saying, give me that in a random order. And if I run that a few times, yeah, at some point it will change the order. So random is kind of the easiest one because it's the least code, but you can just provide custom functions how to sort something. Random can be useful either if you just want to have a sample of the data and you don't really care for the order, you just want to have a sample of what you have. And if I'm sponsoring at a conference and we're doing a giveaway like you just did, that is how we actually draw the winner. So we just say we just want one result back, and we do a random score, and then just one lucky winner will win. That is why I'm always using that one. Okay, and then we have more advanced features in Elasticsearch. So here, for example, I'm saying I'm still searching for father that we had, and now I want to highlight my results. So before my search hit, I want to have this tag, and afterwards I want to have this other tag on the field quote. So if I run that, it will say, okay, I am your father, that is the original, and then it will have highlight for that field, no, I am your tag, father tag. So this is my highlight of my search result. So you can actually easily highlight how this is working. What do you think happens if I do that here? Will it do the same? Let's scroll down. Yes, it does the same, since it's just a synonym, and it even finds the right position. Like previously, if you had white spaces in the terms and you use synonyms, sometimes it would break, but the synonym highlighter was just in the latest version rewritten, so it should be more performant and more stable now as well. And then you can do stuff that looks more like a database. I know this looks a bit scary, and now you wish you had SQL again, because there are so many curly braces. But this is actually quite powerful. So what you can do here is, I'm still searching on my Star Wars index. I'm saying I have a Boolean query, and I have something that must exist. So on the attribute quote, father must be there. And then I have two elements that should be there. Should, so what is in a must that really must exist, otherwise my document will not be returned. The should is just the more shoulds you have, the better your result will be. So if I search that father, you're and Obi, you will see, okay, Obi-Wan never told me what happened to your father, or no, I'm your father. So you will find both of them. They will just be ranked differently. By the way, that is something we should have discussed. if I do scoring and I'm searching father here, one of them gives you this result, 0.41 something, and the other 0.39. Why is one has a higher score than the other one when I search for father? Yeah, genau, the length is the thing. Both contain father once, so the term frequency is the same. The inverse document frequency is also both are searching for father, so that doesn't make a difference. But the length of the first one is shorter, so that is. But the difference is very minor, as you can see. There is still this difference. And by the way, if you search for multiple terms, we have something very fancy called the vector space model. So you just score each document, you kind of draw it out in a vector, and then you calculate which is the closest. And assume we are searching for your and father. Your is very common, so it doesn't have a lot of weight. Or the score is for that should not be that high. And father is much less common. Also in the context of Star Wars, like father is very important and doesn't appear very often in Star Wars. So we can draw that out, and it's a pretty random value, but I just say your has a weight of 1 and father has a weight of 5. So the perfect search document contains both your father. So that here would be the perfect match. And then the question is a document better if it only contains father or only if it contains your? And to actually calculate that, you draw the angle here, and you see this angle is much shorter than this one. So a document that only contains father is kind of more relevant than a term that only contains your. And that is very easy in the two-dimensional space. If you have more dimensions than that, it's harder to draw out, but the concept is the same. You always calculate that angle and see how close it is. Okay, getting back to our queries. And now I can do something like, this is the same query, so it must contain father. My shoulds have 3 attributes, your, obi, and droid. But I also say at least 2 of my should terms must exist. How would that look like in SQL? Probably complicated. You could do it like, you could do all the combinations and or connect them, but this is getting pretty ugly in SQL. So if I run that, it will just find that one, because you can see it contains father, so that is good. It contains your and obi. Yeah, the other one doesn't. And you can even say something has a higher value. So we can boost that. So we can say it must contain father, and it should contain your and obi, but obi is 3 times as important than your. Like boost that by a factor of 3. And then the one that contains obi, you can see that is 1.5, and that is just 0.7. Even though, yeah, otherwise they're pretty similar. But just as obi boosting, if I just put it down to the default of 1, you can see they're much closer together. So you can explicitly say specific fields or specific terms are more relevant than others. You can do other stuff. You can do stuff like suggestions, for example. So if I search for drui, like droid or whatever, just drui, it will not find anything. But I can say, you don't find anything, then give me suggestions what could be there instead of drui. And if I run that, it would tell me, okay, I don't have any matches for the query itself, but I have a suggestion. Like for drui, the closest thing I have is droid. Maybe you want to search for droid. Like that is also a common feature that you probably expect from your search, where you have like, oh, you typed that and that, but maybe you meant this term because I only have this term. I didn't find anything for that other thing. So that is also very easy to implement here. How are we doing time-wise? Okay. Yeah, you can do more complicated things. Like you can do, for example, you can split up tokens into parts. So, for example, n-grams are if you just take a long word and split it into groups of words. And then you try to match as many groups as possible. So for example, if I use trigrams, groups of 3, and I run that, these are not the droids you're looking for, what it will do is we have these, and it will find groups of letters of 3. So D, then this is just these 3 here are just for these. So it will take the first to the 3rd character, the 2nd to the 4th, and the 3rd to the 5th, and build these groups of 3. And that is very helpful if you just want to have partial matches. For example, if you have blueberry in your search index and you search for blue, you would not find anything because there is no direct match. But if you build these groups of 3, you would match these parts of blue like BLU and LUE. They would match. So you would actually find, if you search blue, it would find the blueberry then. So this is just one other tool you can use. So basically, to conclude, I guess, we can go back to our actual example and see what our search looks like. Because I'll make this bigger again. Here, if I open that up, you can see, okay, these were my results. And here under request, I can actually show you what was the query that we issued. And under response, we then have the JSON that was returned as the response. So we're not interested in, we're doing an aggregation. The aggregation is just to fill that left-hand side. So you know, okay, women's clothing, we have that many results. So we're just in one query, we are just getting all the bits and pieces for that page. So we just need to run one query to get all these results. So we're getting, on the category, we're aggregating and we're doing stuff on the color. What we are interested in now is actually the query. So here our query starts, and this is what fills our grid now. We're defining a function score. And I say my query must contain white cotton shirt. I want to have that. Although white cotton shirt will be OR connected, at least half of the terms need to match. And we want to have that in over multiple fields, the results. And here I have the fields over which I'm searching, and you can see right now all of them have a boost of 1, but if I did something like 3 here, the description English would be 3 times as relevant as the other fields. And then you could exclude products, like if you have ever said, I'm not interested in a specific product, you could exclude it here. And then you can filter it further down. If you are interested in, I've said, for example, yes, only give me male products, like that has a weight of 100%. You could say this is less important, or you could switch that to female. You could filter down on ratings, on price ranges. So you can combine all of these features into a single query, and it will just give you a specific result. And that result would then look like something like this. So here, for example, I have sorted by relevance. But if I would want to have just by price, it would just change the sorting of my query, and nothing else changes, and would just run the query. Now maybe the results are not that good anymore. Let's see if I get the cheapest first. If it's ever loading, come on. No, doesn't like my query. Oh, come on. Is my internet? No, my internet is still here. Let's switch that to price low to high. No, that's not a good query now. Okay, something doesn't like my query now. Maybe we can do, oh, now it just was very slow. And again, you can see now, since it's not based on relevancy anymore, like for white cotton shirt, you're not getting great results anymore. But you have sorted by price. I don't know if this is what your user wanted. Like, yes, you can give them that possibility, but maybe you're not really getting the results you were expecting or you wanted. That is unfortunately up to you. Okay, we've pretty much gone through all of those features. The slides will be online afterwards, so you can just start playing around with it. One more thing. Since the Elastic Stack is not only used for searching, we also have kind of an analytics platform built based on top of it in behind the scenes. And here you could see, I'll make this slightly bigger. Here we have just aggregated sales. You could see, okay, we have had that much of revenue. That is how the revenue developed over time. This is what the products we sold. So you can store that data, like all your sales data, in Elasticsearch, and Kibana can very easily visualize that as well. So you can just use the same tools for all of those things. Or I think we have the ratings there as well of the products. And there you could see, okay, reviews by manufacturer. Do I have any manufacturer who gets lots of complaints in comparison to others? And then you see, okay, this product here for man's accessories, that is not getting a good rating. Or Xiaomi for men's shoes, that is also getting a bad rating, and maybe they have some trouble in producing their stuff there. So this is just lots of analytics you can store as well, besides your full text search, and then analyze that. Okay, to conclude, what have we done? We have seen how indexing works. You can format your stuff. We tokenized it, which is basically finding the words. Lower casing, removing the stop words, stemming down to the word root. You can optionally define synonyms. By the way, one very common question is, are there any dictionaries of synonyms you can just use and load? Unfortunately, no, because synonyms are totally dependent on your use case again. You might find some that you can use, but there are no global ones we provide at all. Like, you will need to find your synonyms yourself normally and just define them whatever makes sense. We have seen term frequency, inverse document frequency, field length norm, and vector space model. So if my search term appears multiple times, it's more important. Less frequent terms are generally more important overall. Shorter fields are also more important, and if you have multiple terms, you have this, like we did in a two-dimensional space, but you can see how you actually score multiple terms together. Yeah, we've seen how something like that looks like to, I don't know, analyze your revenue or whatever. And that's pretty much it. I have a lot of stickers over there. Any questions? I don't know, are we going over to the discussion? We have, okay, we can do questions first, okay.
Thank you very much. You told about scoring, but could you get some more details, please, about if there are a way how I can customize the function which produce scores? For example, Lucene allows to customize this function pretty easy, but Elasticsearch doesn't, as I know. Or is there a way, for example, for my personal case, I don't want to take into account IDF function.
That is a common question. I think there is a flag that is not documented where you can actually turn it off. So I know that for some people it doesn't make sense. And I think you have somewhere, there are flags in the Elasticsearch config where you can actually turn off these features, but they're not really documented because for many people it doesn't make sense. But I think you can. You will just need to hunt it down in the source code. Or you can just use a function score. Or our function score is not, you just want to get rid of IDF.
I think for my case, IDF is the only thing which I want to get rid of. And I think there are no enough cases to describe like custom functions for scoring. I know there is a random score, constant score.
Exactly, there's random
so
score,
much.
constant, there's decaying, there's geo. I think there are 5 function scores or something like that at the moment. But maybe you don't even need that. Like in our example, we did the function score. Did you see? Like our example on the website we're using, that is actually a function score, how the query is generated. So if I if I go to the request and scroll down here, you see this is a function score, and then we are just defining that in our own. We're using a boost mode where you can define how you combine it, and then we just combine the query. But all of that is part of the function score, so we can provide a score mode, and then these are the functions how you actually sort it. Is that, wait, I can make that larger. So these are the functions I'm using here, and I'm always saying like the weight is percentage, like 0 to 100. So everything that is 0 right now is not important. For example, I've said the gender attribute is like, that is like a filter. But if you would just say 50% is like, it's 50% more likely to get male products than female products. That is not the TF-IDF thing you want, but that is another way to use the function score. I think there is a flag somewhere, but it's pretty well hidden. I cannot tell you from my memory, unfortunately, but I think it's possible to disable parts of that. There is also in 5.3 there is a new scoring mechanism which is called Boolean, but that gets rid of all of term frequency, inverse document frequency, and query norm. That is just doing the stemming and stuff like that, and then matching yes or no.
Thank you very much.
The question is, do we have anything that would cover for phonetic similarity? Like
Yes.
I type capital O, capital B, 1 is a digit, and expect that it finds me your Obi-Wan.
So you need to install the plugin first. It is not provided by default. And then if you have it, so you have the type phonetic, you have different encoders. There is a dozen or so encoders for different examples. And then I have, for example, checked Obi-Wan. That's the example you had as well. And the metaphone encoder, I'm not sure about the quality of stuff. So it keeps the original and then just does OB and WN. Like that is how it understands it. That is what, but you will need to just take your inputs and try then those with different phonetic analyzers and see if they kind of give you what you want. And it's of course documented. They have something, job logs or something is the example they have there. That is just the installation. Yeah, so here their example is if you have job logs, that is what it would return in that combination. If that makes much sense, I'm always a bit torn. Like in my examples, it didn't help me that much, but maybe this is what you want. So that is the phonetic plugin. You will need to install that, and then you can just run phonetic queries.